Hello everyone, I'm glad to share our work, CR Face, Confidence Ranker for Model Agnostic Face Detection Refinement. I'm Noranath Vesadapan, and this is a joint work with Dr. Bao Yon Wang. Face detection is a fundamental component, and there is a rising demand for faster, more accurate, yet support for higher resolution face detectors. Recent smartphones can record a video in 8K resolution. But many of the existing face detectors still fail due to three main issues. First, a larger resolution increases the chance of generating false positives. For example, some objects, when enlarged, become the same size as face, and it confuses the detector. Second, the existing public dataset, such as wider face, does not contain high-resolution face and cause the large face to break down into multiple smaller boxes. Third, a single image could contain a large amount of very small face. All the challenging cases inspire us to analyze the failure, and we found that most of the correct box locations do exist, because many detectors predict a large number of boxes, but the confidence are very low. We replace the predict confidence with the intersect over union between the predict box and the closest ground truth box and call it oracle confidence, which can significantly increase average precision. In other words, there is a large room for improvement by refining the confidence alone. We formulate confidence refinement problem as supervised learning between the predict and the oracle confidence. We use FVN to extract image features and concatenate with the face detector output on each level of the pyramid. We then add global average pooling and fully connect layer to reduce the dimension to the number of confidence at the end. The refined confidence and original box are then passed into NMS to get the refined prediction. Our design is model agnostic, and it has multiple benefits. For example, during training, we can combine the outputs from multiple detectors to increase the training size. During testing, our method can generalize across multiple detectors. We train our network in a pairwise ranking loss fashion, where we extract multiple predict bounding box and confidence from a single image, then pass them through the same refinement network. We then subtract this refined confidence and train them as a binary classification, where class 1 means the first confidence is higher than the second one, and class 0 is vice versa. Our loss reflect the greedy behavior of NMS, where NMS does not care about the confidence order across different images or the confidence magnitude at all. NMS will simply pick the highest confidence and suppress the rest. In contrast to directly regressing to the oracle confidence, we reduce the problem from regression to local ordinal ranking. We show the importance of ranking loss. While regression can move the confidence distribution closer to the oracle confidence, it does not respect the order because these confidences are very close and a very small regression error can break the order. Ranking loss, on the other hand, does not preserve confidence magnitude but performs better at learning the correct order. The right table shows a significant gap between the ranking loss and all the other losses. We also study the number of pairs, where we start the predict confidence before selecting the pair. A single pair only includes hard pairs, and 100 pairs only focus on easy pairs. 10 pairs yield the best trade-off. On wider face, we show the improvement across 3 backbones, where we outperform single scale, such that we achieve a comparable average precision with multi-scale image pyramid. Multi-scale is the standard post-processing in modern face detectors, and the default setting is 5 scales multiplied by 2 flips, which equal running the detector 10 times. We only need to run a single scale plus our ranker once, so we are up to 12 times faster, and we achieve the state-of-the-art on the single scale. Our method allows us to train on 8K resolution by only running forward pass in the face detector and backward pass inside our network. Without our method, backpropagating 8K resolution in retina face is not possible, even with batch size 1 on 48GB GPU memory. We collect 8K resolution test set to demonstrate the AP improvement. Visually, single scale fails to detect large face. Multi-scale is significantly slower and introduces more false positive. Our method brings back the missing face from single scale and suppress false positive, thus achieving the best result. Thank you.